Hello, in this video I'm going to solve this problem for you on the topic of elementary properties of groups. Let G be the underlying set of a group and let A belongs to G. Define a binary operation star on G so that G and a star is a group with identity element A. That is a good idea to pause the video at this point and give it a try. If you don't want to see the answer before you try the problem yourself, pause the video right now, because on the next slide I will show you the answer. The answer is, we define the binary operation star in this way that for all x and y in G, x star y equals to x, A inverse y. Okay, now let us solve the problem. So you see there are two binary operations involved here. So between these you don't see anything, so it means that I am assuming that this group G, the original operation is multiplication in the sense of group theory, of course. And then I am defining a new operation star based on the original operation in G in this way. So x and y are arbitrary elements of G. A is the element from G which was mentioned in the problem from the beginning. So now I want to show that G with this operation star forms a group in which the element A is the identity element. So let us first of all start checking the axioms of group theory for this binary operation. The first thing we have to check is that this operation is indeed a well-defined binary operation, meaning that G is closed under this binary operation, which is clear. Why? Because if x and y are in G, x star y is this combination, and this operation that you see is the operation of the original group structure of G. So x and y are in G, A is in G, so A inverse is in G, so this product is indeed in G. So this is clear that G is also closed under this binary operation. So this binary operation is a well-defined one. So the first non-trivial one is checking associativity. How should I check that? I would say that, okay, let me take three elements x, y, and z in G and try to convince myself that if I do a star between x and y first and then find the result and star it with z, it will be the same if I apply x on the result of x star z. If I can convince myself of this one, then it means that this operation is also associative. Okay, so I start from the left-hand side. Having this pair of brackets prioritize this star operation, which is exactly what you see defined here. So I just write x, A inverse y, then star z. How should I continue now? When you say x star y is this, how you should interpret that? You should say that, okay, x is the first element, A inverse is the inverse of A, which was given to me from the beginning, and y is the second element. But here, this is your first element, and this is your second one. So what I will do, I will take this, my first element, and put it here, and then I have my A inverse, and then I have my second element, which in this case is Z. Now, this operation is the operation of the original group structure, and we know that it is associative, so I really don't need any pairs of brackets. So let me remove them. So it becomes x A inverse, y A inverse, Z. This is the result of the left-hand side, but let me also do the right-hand side. The right-hand side, the pair of brackets is around this pair, so this will prioritize this binary operation. So for the time being, I copy and paste that part. But now I will do this one. Okay, here the first number is y, so y is playing the role of this x, and z is playing the role of this y. So this becomes y a inverse z. But now this is the first element, this is the second element. So x is playing the role of this x, but this combination is playing the role of this y. So I will take this one, replace y with that expression. So this becomes x a inverse, y is this one. And again, because this operation is done in the original group structure, that is associative, so I don't need any pairs of brackets. So it becomes x a inverse y a inverse z, and then you compare these two, they are identical. Okay, so the left-hand side is indeed equal to the right-hand side. So this means that this operation is also associative. Now, I need to go to the identity axiom. So, but we are supposed to define this in a way that A becomes the identity element. So if I have done everything right, I should be able to show that for any arbitrary x in G, I have to convince myself that x star A is A star x is equal to A. Is equal to x. Yes? This is what I want to show. Because if I have done the definition in a correct way, I have to meet the demand of the problem. So it means that A should be the identity element. Let us see if I have done it correctly. So I start, for example, from x star A. X is playing the role of x, but here A is playing the role of y. Yes, so this becomes x, and then I will have A inverse. Then I will have a y, but y in this problem is A. But in the original group structure, A inverse is the inverse of A. So this becomes the identity element. So if you don't mind, let me call the identity element of the original group structure E. And this is done in the original group structure. So this becomes X. If you want, we can also check the other way around. So A star X. Now A is playing the role of X. X is playing the role of y. So let me have my stick here. Yes, so here A is the first element and X is the second element. So instead of the first element, I put A, but A inverse is a fixed one. So I write it, and instead of y, I simply put x. And again, the same story. A and A inverse are being done in the original group structure. So it becomes E, the identity element of the original group structure, times x, and then it becomes x as well. So this is indeed correct so far. But I haven't shown the full group axioms yet. So the next thing that I have to do is to check the inverse. Okay? For the inverse, if you can guess it, you can guess, do your guess and then prove it. If not, you go to a scratch paper. My goal is to see that, okay, if you give me x from G, can I find another element, let me call it y, so that x star y becomes y star x, becomes the identity of the group. But we realize the identity of the group with the new operation is A. So I am looking for this y. Okay, so let us start with one of them. X star y equals to A. And I am looking for this y. But x star y is this definition. So this becomes x A inverse y is equal to A. But look, we are looking for A. Sorry, we are looking for y. So I have to get rid of them. So I multiply both sides by x inverse. Because it is associative, I don't need to bother about pairs of brackets. And these two now become the identity element in the original group structure. yes? So I don't need to write it, so let me clean it. But still I need to isolate my y, so I have to multiply both sides by a. When I multiply the left side by a inverse becomes the identity element of the original group structure, which gives me y, and then this becomes a x inverse a. First of all, is this an acceptable answer? Yes, because how should I know it's an acceptable answer? I need to convince myself that this y is indeed in G. But that's clear, because G and the original operation is a group structure, so this is closed and that is in G. Okay? So this is the scratch paper work, but if you want to write it formally as mathematicians do, you have to find it and prove your claim. So when I want to do the next, I would say that let x be in G. We prove that this expression, a x inverse a, is the inverse of G with respect to the operation star. Yes? And be careful, this x inverse is the inverse of x with respect to the original group operation. So, in order to do that, how should I prove my claim? I have to take my x and star it with the claimed element from both directions, and convince myself this is the identity element of the group, which indeed was A itself. Okay, of course it will work, because what we did in the scratch paper gave us that. Okay, so what I will do, I will start from here, x star, a x inverse a. So now compare this one with the original definition. X is still playing the role of x, but this combination is playing the role of y. So instead of x, I put just x. A inverse is always there. And then instead of y, I put this expression. Okay? But because it is the original group structure is associative, so I take the pair of brackets and put them around here. So you see what happens. Yes, I don't need to extend it that much. It's simply understandable, because now this becomes the original group identity element, and then I don't need to write it. So it becomes x inverse a, and then again it becomes e a, and it becomes finally a. And the other way around is also the same. Yes? Okay, so here what we did, we had a set with, let us say, multiplication. We had this group structure. I assume that the identity element of this group structure is E. And then I choose another element. Of course, if I choose the same E itself, then E inverse becomes E itself, then X star Y becomes XY. I haven't done anything, okay? So let us say that A belongs to G, and of course, A is not equal to E. If A is also equal to E, this is correct. But the interesting things comes from the cases that A is not equal to E. So we picked an element from this set, and then we designed or defined a new binary operation on the same underlying set, so that again, this underlying set and the new operation we defined forms a group in which the identity element is this a priori chosen element of the group. So, I mean, it's an interesting problem. So let us say that I have a group of finite order. So let us say that the number of elements is n. Of course, one of these is just the identity element. There are n minus one more elements in the group. So immediately, keeping the same underlying set, I can define n minus one other binary operations, so that this structure is again a group. And I can do it in a way that any a priori chosen element of the group now becomes the identity element of this group. So if the order of this group is infinite, I can immediately construct infinitely many other group structures, all of them sharing the same underlying set. So that's an interesting problem, I would say. I hope that you also enjoyed the problem. Okay? So until the next video, be safe and goodbye. Thank you.